you already said the title. Just want to mention that this was joint work between the TU Wien and the Bosch Center for Artificial Intelligence. So what do we do here? Well, we deal with a parallel machine scheduling problem that arises at semiconductor production at Bosch. And our goal is to create schedules, namely robust schedules. So we want schedules that handle changes well, especially new jobs arriving that were not previously known, or a machine failure where all those jobs on the failed machine have to be scheduled somewhere else. Now, and the way we do this is we lexicographically minimize the machine span, starting from the largest to the smallest. And this idea was actually recently introduced in a paper from 2021, so this year actually, where the authors introduced this objective with the same informal goal. So they also have robustness in mind, and one of their conclusions is that this lexicographical minimization achieves exactly that. So it creates robust schedules that handle updates in a good way. Now, what we use as our solution approach is antecedent programming, which, as I think most of you or all of you know, as a state-of-the-art logic-based KRR paradigm. And in particular, we use an extension of antecedent programming, where we additionally have a theory, namely difference logic. So our scheduling problem concerns unrelated parallel machines. This unrelated means basically that the jobs do not need to be performed on several machines, but only on one. And the machines have different efficiencies. Now, the jobs are non-preemptively scheduled. So once they are started, they cannot be paused or stopped. And we have dedicated machines. So what this means is that a job cannot necessarily be performed on every machine, but only on a subset of the machines. Now, a job also has particular properties that vary from machine to machine. So one of them is the duration, because we have different machine efficiencies. For example, the duration, of course, varies. Now, we also have a release date on each machine for the job, and we have particular setup times, which are sequence dependent. So what this means is that the order is actually relevant. So if you change from one job to another job, there is a particular setup time that is needed from that job to the next one. So maybe to explain this a little further, here you can see an example schedule where we have 3 machines and 7 jobs. And if we pick out one job here, it would be job 4. Then this job has 2 capable machines, so 1 and 2, meaning that it has to be assigned to either one of those, but it cannot be assigned on machine 3. Now, it also has a release date on each machine. Here you can see the release date on machine 1. What this means is that it can only start after the release date. So as you can see here, this is also satisfied. Now, for the total processing time of a job, it basically consists of 2 things. So we have the setup from the previous job to this job. So here it would be the setup from 1 to 4. And then we also have the duration on the particular machine. So here it's duration on machine 1. Now, as I already mentioned, what we want is we want to lexicographically minimize the machine span. So, and informally, what this does is that we ensure that each machine finishes as early as possible. And this objective we also call the Lex Makespan for lexicographical makespan. So how does this look like? Here you can see 2 schedules. On the left, we also have indicated the makespan, and on the right, we have indicated the Lex Makespan. And the makespan is actually equal for both schedules, but the one on the right has lower Lex Makespan, as you can see, because machine 2 and 3 finish earlier. And the reason why we care about this is because if we would only consider the normal makespan, then there is no constraint on when machines 2 and 3 would need to finish. So it could be that a particular machine basically dominates the makespan, and all the other machines could be drawn out, or their spans could be drawn out unnecessarily. And the Lex Makespan objective makes sure that this is not the case. So really every machine, the span of every machine gets optimized, so it's as short as possible. Now, our solution approach is answer set programming, which means we make use of standard ASP rules, which consist of a disjunction of atoms in the head and a conjunction of atoms or default negated atoms in the body. And since we use this difference logic, we also have difference constraints, which can appear in the rule head. So a difference constraint consists of a difference term on the left-hand side over two integer variables. So here it would be a and b. And on the right-hand side of the constraint of the term, we then have a constant, which basically acts as a bound to the difference. And the nice thing about those constraints is that they can be decided in polynomial time. What we also use are domain heuristics, particularly the domain heuristics in Klingo that allow us to specify domain knowledge in a declarative way, in particular on how the solver should make the assignments or which assignment should be preferred in a way. Now, solutions are then, as always, sets of atoms, but since we also have those integers in integer variables in the difference constraints, we also have value assignments to those integer variables. And the system we use for this is KlingoDL, which is an extension of the well-known Klingo ASP solver with the difference logic theory built in. Now here you can see our ASP encoding. I'm not going to explain everything here because I obviously do not have the time, but feel free to ask us later at the poster session or just check the paper. What I want to say is that we can use standard ASP rules to model the job assignments, so where a particular job gets assigned to which machine, and also the job order. So we have basically permutations of jobs on all of the machines. And we use the difference logic to encode something else, namely the timing information. So there's an integer variable for each job that indicates its completion time. And then we can express all the constraints that are over those completion times. So for example, the first constraint here says that each job can only start after its release date. Now, we also use heuristics, as I already mentioned, and we have two ideas how such heuristics can be involved in the search. So the first one basically expresses that we want to prefer assignments of jobs to machines where the duration is low. So we use those heuristic directives basically to tell the server that it should first try to assign a job to the machine where its duration is the lowest. Now, and we also do something similar for the setup times, where we intuitively tell the solver to align the jobs in such a way that it picks the one that it aligns them next to each other if they have a small setup. For the lexical Makespan optimization, we have different approaches on how to encode this. One of them uses the standard Klingo optimization. Now, since those integer variables in the difference terms, they cannot be used in the standard minimization directive of Klingo. So we have to use a little trick. So we basically just guess the machine span of each of the spans, which basically acts as an upper bound. This upper bound can be then again encoded into difference logic or with a rule using the difference logic term. And then we can minimize over this guessed span. And as a priority, we can just use the span itself. This actually kind of elegantly allows us to express the constraint that the highest machine span is actually the most important objective, basically, and then the second highest and so forth. Now, another way to do this is by employing multi-shot solving. So here in the first step, we would optimize for makespan. And after we have achieved an optimal makespan, we would fix the value, not any of the jobs, but only the value of the makespan. And then we would proceed to minimizing the second highest span. And we do this until either we have minimized all of the machine spans, so they're all optimal, or if we reach some timeout. Now we evaluated our approaches empirically on a set of randomly generated benchmark instances, namely 500. and they have different sizes. So the number of machines ranges from 3 to 20, the number of jobs ranges from 5 to 200. And for the machine capabilities, we have either assigned them uniformly at random for half of the instances, or for the other half, we pick the capabilities in such a way that 80% of the jobs can only be performed by 20% of the machines. So this creates some kind of high dedication instances. Now, to provide additional comparison with MIP and CP, we also provide a mini-sync model, which can be used with different solvers, and dedicated CPlex and CPU optimizer models. And because in the setting in the factory, they schedule very often and only have a short time, we picked the timeout of 5 minutes for each instance. So here you can see some of our experimental results. On the left-hand side, we would have as kind of a baseline standard Makespan optimization, and on the right, you can see the results for our Lex Makespan objective. So you can already see that for Makespan, ClingoDL performs very well. So it outperforms CP solvers like R2s and G-code, and also CP optimizer, as well as the MIP solver CPlex. For Lex Makespan, this is not as true anymore. So CPlex and CP optimizer perform a little better than the standard ClingoDL optimization. However, if you use our multi-shot solving approach, then we again achieve the best results. Now, to conclude, we started the application of hybrid ASP to solve a challenging parallel machine scheduling problem. And it turned out that the problem can be elegantly modeled using ASP, and the results are competitive with other MIP and CP solvers. Now, the usage of heuristics and multi-shot solving enabled us to achieve very good results, outperforming state-of-the-art solvers. However, even though ASP with difference logic is kind of promising for scheduling, it still has some slight expressivity issues. So it's not so easy to express complex objectives, like, for example, total weighted completion time. So this is something that maybe can be improved. So as future work, we'd like to address those expressivity issues and also study hybridization techniques of ASP with meta-heuristics or just meta-heuristics for this parallel machine scheduling problem. Thank you for your time, and I'm happy to answer any questions.